Unit Operation Classroom. And this is an initiative of unitoperation.com, and we are discussing GATE 2023, question 35, and I'm Shekhar Bhattacharjee. In a binary gas liquid system, NAEMD, that is their nomenclature, is the molar flux of a gas A for equimolar counter diffusion with a liquid B. So let's say, of course, there is a gas liquid interface here, and they're assuming that A and B are moving in two opposite direction, but equimolar in the sense that Na is equal to negative of NB. So the values are the same, just but in the opposite direction. And NaUm is the molar flux of A for steady one component diffusion to a stagnant B. So if you have a stagnant B layer, let's say, and A is diffusing through it. So that is an example of NaUm, the molar flux of A for steady one component diffusion to a stagnant B. We'll try to see some practical examples of what do they mean. Using the mole fraction of A in the bulk in the gas phase at zero point 0.2, and that at the gas liquid interface at 0.1. So this is a gas liquid interface here, and in the bulk gas here, of course, this is 0.2 and this is 0.1, and of course we have to find out the ratio of if there's a NaEMD and NaUMD. That means in one case, it's let's say it's this equimolar counter diffusion, and in the second case, it's a molar flux of A, is a diffusion of A through a stagnant B medium. So what's the ratio of the two? So these are very standard equations, and if we just take the ratio, it's just this is the term which comes out. And by definition, of course, this is this one right here of log mean, and we know YB1 if YB2 is this one and YB1 is this one. So since we know that this is at this is equal to 0.2 at the bulk, so YB1 0.8 and YB2, which is at the interface, this is 0.1, so that is 0.9. So we can calculate this one using this formula here. So this is the rate 1.178. So that is the answer. This is a very simple and standard problem. And I would say that just read a very good textbook to clear your concepts. So these videos are only helpful to understand one particular problem, but they don't give you a clear concepts of the entire theory. Okay. Now, let me try to give you a very quick approximate example of NaEMD and NaUMD in practical applications. Let us take a distillation column here, and let us respond this particular tree where this is a pool of liquid. Let's say this is a benzene tolerant binary distillation, and then the gas just flowing through it. And there's, of course, an intimate contact of the gas and liquid. If we just take this one, and if we just take this one and kind of expand this one here, so basically, as you can see, there are a lot of bubbles, and each bubble contains, of course, benzene toluene, and the liquid also contains benzene toluene. So if we just again expand this one particular bubble here, so let's say this is my gas bubble, so this is my bulk gas here, okay, which of course contains benzene and toluene. And right after that, there is a very thin gas film. And this is my interface. This dotted line is my interface. So this is the bulk gas, and this is the gas film. And around this one, there is again a very thin liquid film. And after that, that's a bulk liquid, which is the bulk liquid right here. Okay. As you can see, since benzene and toluene have almost equal molar latencies, which is a very standard information, what will happen is that, let's say, in this particular gas film, the toluene will tend to go from the bulk gas to the liquid, the bulk liquid, and of course, benzene will tend to move from the bulk liquid to the gas. And so that way, this becomes enriched as it moves upward in the enriching section. So, if we take this gas from here, so there's a movement of this is the toluene here, and this is the movement of the benzene. So, toluene diffuses from towards a bulk liquid, and benzene diffuses towards a bulk gas. And of course, the molar flux of benzene is going to be the same as molar flux of toluene, but just in the opposite direction here. Okay, so that is an example of EMD. Let us try to see again with the same benzene and toluene what could be an example of UMD. Let us say this is my tank here, and in this tank there's a benzene toluene mixture here, and so there of course is going to be a very thin film of liquid, and then there will be there'll be an interface here, and of course after that there is the gas film. And let us assume there is no disturbance here, so this gas film remains pretty much steady. And since toluene has a much higher boiling point, that does not move. Why it does not move? Because in this one, we are assuming there's a very large flow of nitrogen or air that is sweeping on the top. And so benzene is because of the partial pressure difference here, the partial pressure at the right at the surface is the vapor pressure of benzene at that temperature. And here, since there's a very whatever benzene comes out, it gets blown away. So we can assume the partial pressure of benzene is equal to 0. So there's a constant gradient, that is a constant transport of benzene from the liquid surface towards a flowing stream here. So, if we assume this toluene as a very, of course, with this one assumption, this is a fact. Toluene is a high boiling point, but we're assuming that this toluene literature remains pretty much steady and does not move. So that would be a constant, that would be a stagnant toluene there, through which benzene moves towards top on this one. So this is an example of benzene moving to a stagnant layer of toluene. So this is an example of UMD. Okay, so anyway, these are just approximate examples of practical applications, but the answer, as we said, this is equal to 1.178. That's the answer.